just, I just have to say this in reference to Brett's talk. During her talk, I texted Robin Canup about her no slide. And Robin says, oh, I'm so glad she didn't say no to the decadal survey, right? So, okay. So it's really exciting to be back here again. The name of our team is the Center for Lunar Origin and Evolution, or CLOE. This name means a lot to me because this is the name we came in when we were part of the original NASA Lunar Science Institute. So this is sort of like returning to the beginning in some sense and being able to be involved with this again. Okay, so I can never get through this talk on time, so I'm going to be very fast on certain things. We have a fantastic team of scientists. We have 18 COIs. The majority are from Southwest Research Institute, but we also have fantastic scientists from the University of Arizona, the University of Colorado, Jet Propulsion Laboratory, Purdue, Yale. So we're hoping to be able to do all sorts of exciting things over the next 5 years. Okay. So our team has 3 main science themes. Okay, I'm going to go through them and some of the tasks and some of the motivation of what we did. Our first theme is terrestrial planet formation and early lunar bombardment. Okay, so the issue is this, right? So ultimately, we'd like to understand the formation of the moon. You cannot understand the formation of the moon without understanding how the terrestrial planets formed. Right now, our terrestrial planet formation models have issues, okay? One of the big issues is trying to figure out how do protoplanets and the rest interact with the gas in the solar nebula, right? If models don't include this, we get simulations kind of what you're looking at right now, where the protoplanets are growing all across the inner solar system, but we end up with terrestrial planets which don't have the right separation, and our Marses and Mercuries are way too big. Okay, so this is a big issue. We've been trying to figure this out for decades, come up with all possible solutions, and we're still not quite there yet. Okay, so the latest and I would say really interesting mechanism that's come into the field that I think everybody excited is something called convergent migration. So this is the idea that protoplanets, when they get large enough, start to interact with the gas disk, but depending on the conditions in the disk, the temperature of the disk, the density of the gas, and every such thing, you can actually get objects not just migrating in one direction, but migrating in different directions. And in some cases, you can actually have things migrate towards 1AU, okay? But only the large guys, the small guys stay behind or so. So this might be a way to get the right size Mercury and Mars, but also it relates to how big the impactor is that made the moon, or what we call Theia. So where did Theia form? How big is it? We need to understand terrestrial planet formation for that. Okay, so here's a test simulation just to give you a feeling for things. Here you're growing protoplanets in the disk, but you can see they're actually going to 1AU. So we're building up things there, but everything else is kind of staying small, right? So this may be the pathway to give us some idea of where Theia came from that ultimately ended up hitting the Earth to make the moon. Okay, a second issue has to come with what I've been talking about for many years now, which is what's called the giant planet instability. Okay, so the thinking is that our giant planets formed in a different configuration than what we have today. And then they went through an instability and they migrated their current orbits. In the process, not only did they destabilize all the small body reservoirs in the solar system, but in the process of migration, they destabilized a lot of material in the inner solar system as well, where the terrestrial planets are forming. So you can't do terrestrial planet formation without worrying about the giant planet instability if our current thinking is correct. Okay. So here's a simulation, just to give you a feeling for this, where we put in a giant planet instability early on. So Jupiter is migrating just the way you saw before. What it's doing is adding an extra level excitation to the inner solar system. And so what happens is that you actually, make terrestrial planets, and some of our terrestrial planet systems get very similar to what we see today in these simulations. So this is very exciting. Okay. The other thing is you'll notice that there's all these like white dots flying around over here, right? These are what are called leftover planetesimals. These are things that formed in the terrestrial planet region, but didn't get accreted right away. So when you have a moon forming impact, these guys are going to be around to beat up on the moon. So it could be that our earliest impactors on the moon are from this population. Okay. And in fact, in some recent papers we've done with David Nisforny, where he's the lead author, he's actually looked at the contribution from different populations, and it looks like the leftover planetesimals may dominate. So if you're looking for what made South Pole Lake and Basin, for example, it may have come from leftover planetesimals. But this raises all sorts of important questions that we're going to hope to address in our team. Okay. So first of all, when does the moon form? Does it form early or late? And there's interesting implications for both. What is the length of the lunar magma ocean? Because the lunar magma ocean could potentially erase early evidence for basins and the rest, but how much can it erase, right? This model suggests there should have been lots of impactors hitting the moon that are capable of making South Pole Lake and basins, but we only have one. So did a lot of early basins get erased, Or did the moon form so late that it just didn't get hit because it wasn't there, right? What is the age of our South Pole Aitken Basin? That's something we're hoping to address in lots of different ways, but dynamically, can we say something about that? And then finally, the projectiles that are hitting the moon early on, they're these leftover planetesimals, they're the precursors that we've been missing in our meteorite collection to try to understand the nature of the early Earth. So can we get traces or samples of these objects that can help fill in our picture of what it takes to make the Earth and Venus and Mercury? Those would be big questions to answer in some fashion if we can do it. Okay, second theme. Second theme has to do with revealing the conditions of Earth-Moon origin, okay? And so here the issue is as follows. So imagine now you had a giant impact that makes the moon. Then the question is, well, how can we say what happens to, how do we know if we have the right simulation? Well, something that's been Robin Knupp will call a crisis in our issue with making the moon is that the isotopic signatures of the Earth and moon are remarkably similar in all of these different elements, right? No one understands how that can happen. There's been all sorts of suggested solutions in the literature in terms of giant impacts, but those different giant impacts vary by at least a factor of 10, okay? And the impactor mass they needed and the impact energy involved in making our moon. So our goal here is to try to link these kinds of models to predictions, right? So ultimately, we're going to try to take the observable properties of the moon, and we're going to try to test which giant impact models can really end up giving us our moon, not just any moon, but our moon. And also, what data do we need if we're going to continue to, if we need to resolve this model, or we need to resolve our ideas even further, okay? So we're going to do this in 3 parts, right? The first part is we're not going to start with giant impacts. We think a lot of those have been done. We're going to start with making the moon. So imagine you create a protolunar disk after the giant impact. It's effectively a magma vapor disk that's interacting, making moonlets, ultimately making the moon, right? So how does that disk evolve? How do we get evolution in that disk? And how does it change as a function of different giant impact models? So that means we have to worry about all this complicated evolution, but also the pressures and temperatures and the material in the disk and all those sorts of things, right? So we're going to make a moon from that. Okay. The next thing is we're going to have to worry about the chemistry of the moon. So all the things I just talked about, all the dynamical behavior has to be linked to a chemical model. How much, let's say the moon's disk has a lot of volatiles. How much of those volatiles end up in the final moon? What volatile content does the moon lose? There's all sorts of other examples you can give on this, right? So can we put all this together to make a moon and then compare it to constraints? And ultimately, do we need more constraints coming from the latest samples coming from Artemis and what have you? Okay. The final constraint you can put in is how the moon evolves away from the Earth. So imagine right after you have the giant impact, you have a hot Earth. You may even have a short-lived magma ocean on the Earth, but the Earth is very, very hot. The moon is recession from the Earth is affected. Angular momentum exchange is affected by the temperature of the Earth. The Earth's rotation rate is changing as the moon recedes away, but that's a function of a lot of properties of the early Earth. So we're going to try to couple models of Earth's cooling, the morbid orbit evolution of the moon, and how they interact from an angular momentum perspective. And can we lead all that to get our moon system an early bombardment, okay? So in terms of South Pole Aitken Basin, I think most people in this room would say that South Pole Aitken Basin is the biggest basin on the moon that everyone agrees is a basin, right? There's lots of I can say on that. It's over 2,000 kilometers across. Now, what everyone knows is the Artemis landing sites are near the lunar South Pole, but they're also very close to the South Pole Aitken site. So that means all sorts of interesting things in terms of what the astronauts might be able to get from South Pole Aitken Basin. Also, in the decadal survey, which I was part of, the Moon Committee made a really interesting argument for a concept study called the Endurance A rover. This is a long-distance rover that would be landed in the middle of SPA. It would drive across, collecting samples everywhere they go. And some of these samples might represent lunar mantle. Some of them might represent bombardment fragments that would tell us about the early moon. They might tell us about the bombardment population, all these sorts of things. So it's a fantastic concept, and it was actually rated the top objective or top priority of the lunar exploration program. So the question is, how do we do science in SSERVI that helps optimize those 2 incredible opportunities that may be coming up in the near future? Okay. So one possibility, so one issue is to really understand the nature of South Pole Aitken Basin, but that means going back to the beginning. And by the beginning, that means we have to sort of reconstruct the moon, not the way it is today, but what it was. So can we put, so essentially put back together all the basins that we see on the moon, put them back into a pristine state, and then from there model the origin of SPA basin from what the primordial moon must have been like. Okay, so we're going to try to do that with a variety of different geophysical methods and impact models. And ultimately, we're going to look at how do we make SPA basin? How do we get this right shape, this right structure, but also where does the ejecta go? Okay. And one of the ways we're going to do this is we're going to take some of the most advanced versions we have for shock physics hydrocodes. So we're going to use the 3D version of ISAIL for this, and also a smooth particle hydrodynamic code to follow where the ejecta goes. And we're going to ultimately see, where would you expect to see exposed mantle? Where would you expect to see all these different properties we're talking about? And then we're going to constrain this by looking at gravity data from GRAIL, from topographic data, basically all the other constraints that the other teams are doing. We're going to try to fold in to see which of our models gives us the right SPA and where all that stuff went. Okay. Another issue with endurance A, I keep saying endurance A because that's from the decadal SSERVI, but I'll just say endurance, right? The thing with endurance is that endurance is going to go collect samples, but it's likely that the samples are not going to be huge. They're going to be little small guys, right? But what we know even from Apollo is that some small objects are better for doing science than others. Some rocks are very shocked, some have issues and the rest. So what we're going to do with our team member, Carolyn Crow, is we're going to try to find samples which we would call endurance size samples in the Apollo samples, in the lunar meteorites. And then what we're going to try to do is do science on them and see what are the telltale signs we need to get the most science out of the samples we collect, and which one should we avoid. Okay, so we'll be doing lead, argon, and various exposure ages of these rocks, and then ultimately trying to do some science with them as well. Okay. Finally, what our last thing is you can imagine all the endurance samples coming to the Artemis landing sites, but because Orion has mass issues, they may not be able to take all the samples back, which would be a pity. Okay, but what we may need to do then is some triage at the site. You can imagine astronauts doing triage on the samples. One way to do that would be to have some kind of in situ dating method. So our leader of this project, which is Scott Anderson, he has what's called the chemistry and dating experiment, or CDEX. Okay, what it is it fires high-powered lasers, vaporize some of the sample rock. That rock is injected or is ingested by the CDEX. It goes through a mass spectrometer, and ultimately we do rubidium strontium dating on that. So what we want to do is test to see how good that device is for various terrestrial and lunar samples. What are its limits? What rocks are good to date? What rocks are hard to date with this mechanism? Okay. And what's exciting is you'll hear more about this later, because Scott Anderson recently won the PRISM call, his mission Dimple, he'll be talking about in a bit. And he's going to actually be doing in situ dating for one of the young Mari patches that are very much like the Ina region. Okay, I think I'm just about out of time. Okay, so I'll just say we're doing also a number of things for community inclusion and public engagement. We are partnering with several different existing programs. We're partnering with NASA's Neurodiversity Network. This is a fantastic program where they're interacting with students that are on the autism scale. We're going to be working with them and seeing how we can bring them into science. We have work with the Ad Astra Academy, which is basically bringing real life science to students in rural and under-resourced communities. We're doing work with the Summer Science Program. This is a fantastic program where they bring in really gifted high school kids from all across the country for 6 weeks, teach them about astronomy. They teach them about how to observe near-Earth objects, do the math behind this. We get involved with the students and do things with them. And finally, we're involved with the Planetary Reach workshops, which try to reach out to educators that serve Black and Latinx communities. We're going to try to see what we can do to get more planetary science into their curriculum. And so with that, I'll stop. Thank you.